All right, recording is rolling. Welcome to Wednesday, March 22nd. So you guys remember yesterday, I took you guys through 6 of the 10 puzzles on this page, chapter 12, thermodynamics. You guys remember this? Before I get rolling too far, does anybody not have this page and needs it? Anybody not have this? All right, so here's what we do today. We're going to do these last 4 problems, and then we'll switch over and I'll give you guys a PowerPoint presentation on nuclear energy. All right, so a reminder how a lot of these problems were working from yesterday, and we're about to continue this. You guys remember this phase change diagram? So temperature versus internal heat energy. Okay, so go to the right, that's more internal heat energy. Go up, that's increasing temperature. And the last one that we did yesterday is actually a pretty good story for this. Right? So the very last problem we solved yesterday was you pull out a very cold ice cube from the freezer. That's about this point right here. You throw it on the stove. So it absorbs heat energy and warms up to 0 degrees Celsius. And then something funny happens. When it starts to melt, its temperature stays stable at 0 degrees Celsius. And the length of this leg of this phase diagram is called the latent heat of fusion. Once it completely melts, go ahead. It's very cold water. Right? Now keep adding heat energy to it. Now the temperature starts to rise again. That happens until it hits 100 degrees Celsius. Now that would be true for water at 1 atmosphere of pressure down here at sea level. Okay? And then it goes through this boiling process. And again, the temperature stabilizes until all the water is completely evaporated. And then if you could somehow still heat that steam, then the temperature is allowed to go over 100 degrees Celsius. That's okay. It'll happen in those stages. Okay, so that's a quick reminder. Point we're picking up from. So that next problem is number 65. We'll do the same way we did yesterday. I'll solve mine, and then I'll give you guys a minute or two to solve yours, and you guys can help each other out too. Number 65. I have a 10 gram lead bullet. Here's the specific heat capacity of lead. It's a very small number compared to water. Remember, water is 4.18 joule per gram Kelvin. And metals are like point something. Here's lead has a very small heat capacity. What that means is that it's very easy to change the temperature of lead. You put in a little bit of heat energy and it changes its temperature by a lot. So this lead bullet is moving at 250 meters per second, probably because it's been fired from some firearm, and then slams into a tree and is brought to a stop. Okay? If its kinetic energy had been converted completely into thermal energy, and furthermore, let's say that thermal energy had been contained completely within the bullet, then how much would the temperature of that bullet rise? Right. So a few things I want to tell you guys here. One is that you guys usually this is going to be conservation of energy. Kinetic energy is going to go completely into thermal, which reminds me a lot of yesterday. You guys remember the waterfall yesterday? So that water splashing out, it went from potential energy to thermal. Right. So this one's kinetic energy to thermal. So very similar principle. Another idea is that where actually would that energy realistically be diverted? And I'm thinking of a few places. One is that it probably some work equals force times distance into pushing away those wood fibers so the bullet can embed itself in the tree trunk. Another place is maybe probably a thermal energy temperature rise in the wood itself. And then the third place that we go is into the temperature increase of the bullet. Now, the assumption here is that all the energy stays in the bullet and it all goes into the temperature rise of the bullet, which maybe is not completely realistic, but what it is good for is maybe an upper boundary condition. So in this class, one thought process you can get out of a class like this, taking a class like this, is to think about boundary conditions. So maybe a better wording for this question would be, what would be the maximum temperature rise of this bullet? So that's what we're solving for. Let's do this. Number 65. So this is going to be conservation of energy. Sum of energy initial equals sum of energy final. Okay? And the initial energy in this case is kinetic. That's 1/2 mv squared. And it all goes into the thermal energy of the bullet. That's mc delta T. Where you guys remember M is mass, C is specific heat capacity, and delta T is a change in temperature. You guys remember that? Okay. Now, before I even get going too far, do you guys see that something's going to cancel out? What cancels out? The mass of the bullet. Now, I did tell you the mass of the bullet, but I didn't have to, because even if you had a bullet that was like twice as massive, the fact it's moving at the same speed, it comes to a stop, blah, 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 whatever the temperature change would be, looks like, oh, it's going to be independent of that mass. So we don't even have to plug in the mass. There actually is one more trick you need to get this right, which is I actually gave you a specific heat capacity in units that are not exactly applicable here. This is in joules per gram Kelvin. Do you guys see that over this page, I'm kind of mixing, matching. There's some grams, some kilograms. And ever since August, we've strictly been using kilograms because kilogram is the base unit of mass. But here, this is joules per gram Kelvin, which is actually going to cause a bit of an issue because we're mixing, matching thermal energy with kinetic energy. And this kinetic energy, even though the mass cancels out, it's implied for joules that kilogram is embedded in that energy quantity. So we're gonna have to use joules per kilogram Kelvin for the C. So we have to do a little conversion here. Whoops, what am I doing? I meant to just go ahead and start plugging in numbers. We do that. So 1/2 time. Now the speed of my bullet was 250 meters per second. Don't forget to square that. Is equal to right. Now here's where we're gonna make this change. For C, specific heat capacity, instead of 0.159 joules per gram Kelvin, do this. Do 159 joules per kilogram Kelvin, right? And this is all multiplied by some delta T that we're solving for, and we're just gonna solve for delta T, right? What's the temperature rise? Okay, okay. Guys got that? Okay. So one algebra step. I'm gonna take this 159 joule per kilogram Kelvin and divide that down. Okay. So delta T is 1/2 is 250 squared over 159, and that would be some Kelvin or degrees Celsius, since it's a temperature change. That's perfectly fine to say too. So I'm getting a change in temperature of 197 Kelvin, or I could call that 197 degrees Celsius. Temperature change. Okay. You guys a moment to chat. Make sure you guys are getting an answer choice on your page. It's all working out. All right, you guys all good? All working? All right, ready for the next one? All right, number 70. What's the minimal amount of ice needed to cool 250 grams of tea from 90 degrees Celsius to 0 degrees Celsius? Ooh, that is some scalding hot tea. 90 degrees Celsius. Isn't that like almost boiling? Right, that's 10 degrees away from boiling. So I need a mental model to solve this one. Okay. We've got this really hot tea and we want to bring it down to 0 degrees Celsius. So let's do this. If I got really hot tea that's almost boiled, it's 90 degrees Celsius. Isn't that like right here on this phase diagram? We're going to use water as a stand-in for tea because tea is basically water, right? Okay. And I'm going to throw in some ice. Now, the thing about the ice is I have to choose what kind of ice I'm working with. I mean, if I chose ridiculously cold ice, I probably wouldn't need very much ice. The wording in that question, now that I'm looking at it, probably isn't the best wording because what's the minimum ice you need? Well, you could have like 0 Kelvin ice and then you wouldn't need very much, but we're not going to do that. We're going to say our ice is like right here. Okay, we're going to have some ice that is at 0 degrees Celsius, but it's completely frozen, but it's on the verge of starting to melt. Right. So the 2 points I'm looking at on this graph are I have some 0 degree ice right here, and I have some 90 degree tea right here. And the tea is going to transfer its thermal energy into the ice. And I'm going to have it so that they both reach equilibrium right at this point. Is that okay? Okay. So we're going cold ice here, or maybe I should say, we've got some ice right here. We got some tea right here, really hot tea. Okay? And then there's going to be a thermal energy transfer, and you're going to reach equilibrium right at this point. Okay. number 70. Okay, this is also a first law of thermodynamics question. So the heat energy lost, or no, I should say gained by the ice is the same as the heat energy lost by the tea. Okay. Right, now, I'm guessing for the tea, since the tea is in the liquid phase, I know that that's some version of MC delta T. Okay. Mass of the T times specific heat capacity of, well, I'll use water for this because standard for T, right? Times the change in temperature of the T. Right? Now for the ice, there's a reason I did the T first. Right? I'm not going to do MC delta T for the ice. Now, why is that? Well, because there is no change in temperature of the ice. If you're going, because you're going from this point here to this point here, what's the temperature change? Well, there was no temperature change. You guys see that? We have all solid ice here and all melted away here. Okay? Oh. So you don't use specific heat capacity. What you use is latent heat of fusion. You guys remember these 5 numbers from this table from yesterday? Okay. Latent heat of fusion, which tells you basically the length of this part of that diagram. So that's mass of the ice times latent heat of fusion. Okay. You guys got that? So what's a good next step? We are solving for how much ice would you need to make this whole thing happen. So massive ice times latent heat of fusion. I'll go ahead and plug a number. Why not? We're going. It's 334 joules per gram. Okay. Then on the other side, mass of T. Oh, did I tell you guys why I did a negative? Because whatever energy was lost by the T is exactly picked up by the ice if it's a closed system. So it's like an import-export thing, right? Okay. So mass of the T, I have 250 grams. Specific heat capacity of, well, T water would be 4.18. That's joules per gram Kelvin. And the temperature change, well, it went from 90 degrees down to 0 degrees. So final minus initial will be 0 degrees Celsius minus 90 degrees Celsius. Okay. Now that would create a giant negative number, but don't forget that there's also negative slap on the outside. So the negatives are going to cancel, makes it positive. That means we can get a positive mass of ice, which is a good story. Last step, I'm going to take the 334 joules per gram and divide it down. So mass of ice is, let's see, 250, 4.18. 90, all divided by 334, then negatives cancel. So this would be some number of grams of ice. So I'm looking at 282 grams of ice. Of course, that's assuming that my ice was at 0 degrees to begin with. If you are very observant, you might even notice that the mass of ice is greater than the mass of the original tea. Huh. So by the time this mixture mixes down, you'll have like super diluted tea, wouldn't you? Actually, I pulled these questions out of the textbook, and there was a follow-up question about that. It's like, how they worded it, it had something to do with that concept. Oh yeah, I remember your textbook is saying, should you let the tea like sit in room temperature for a while and cool down first before you put in the ice? And that would make sense because then you wouldn't have like a bunch of ice compared to the tea. How many of you guys need more time on this one? Okay, you guys good? All right, next one, number 71. A block of copper at 100 degrees Celsius. That is some hot copper. I wouldn't want to touch that. That could burn you. It's brought into contact with the block of aluminum at 20 degrees Celsius. That's like room temperature. Oh, you know what? Pause right here. 20 degrees Celsius. I've been telling you guys that's about room temperature, but you know what I haven't done with you guys yet that I'm going to do right now? Let's do a temperature conversion. Do you guys know how to convert from Celsius to Fahrenheit? Let's say you do vacation in England over the summer and say it's a jolly 18 degrees outside today. Like, what is that in American? Do you guys know how to convert that? So the temperature in Fahrenheit is equal to, let's start with temperature in Celsius, like 18 degrees Celsius. Multiply the Celsius temperature by 9/5, and then add, actually, I'm not even gonna tell you guys. I bet you guys can figure this out with critical thinking. Suppose it was 0 degrees Celsius outside, like really cold winter day, 0 degrees Celsius outside. What would be the corresponding temperature in Fahrenheit? 32. Ah, so what do you have to add at the end of this? 32, right? There you go. There's how you convert from Celsius back to Fahrenheit. 9/5 of the Celsius temperature plus 30. So let's try this out. So what if it was 18 degrees outside? So what is 9/5 of 18 degrees plus 32? That corresponds to about 64 degrees Fahrenheit. Okay, about 64 degrees Fahrenheit. Wouldn't that be? So what about this particular problem? We're looking at 20 degrees Celsius. 20 degrees Celsius. That is like 68 degrees Fahrenheit. You guys that? Okay. And if you're not walking around with a calculator in your pocket and you want to like a quick conversion, then guys, 9/5 is really close to what integer? 2. That's almost 2. It's a little bit less than 2. So 2 would be an overestimate. And then if you said plus 30, the 30 would be a little bit of an underestimate. So let's try this again. So let's convert 20 degrees. 20 degrees Celsius, we already know is exactly 68 degrees Fahrenheit. Well, if you did the times 2 plus 30 method, so 20 times 2 is 40, plus 30 is 70. Ooh, 70, that's very, very close to 68, isn't it? So that's good, good estimate. And tell you what, just for completion, temperature in Kelvin is temperature in Celsius. Let's say equals. Temperature in Kelvin is equal to temperature in Celsius plus what number again? 273. Okay, you guys know that? All right, let's get back to this actual question though. I should have asked you guys a temperature conversion question on this page somewhere. Oh well, we did it. And so I got a block of copper at 100 degrees Celsius, blocking that I brought into contact with a block of aluminum at 20 degrees Celsius. Let's see, focus here. Here's the specific heat of each of those metals. There are 2 different metals. Okay? And I'm telling you that there's going to be some final equilibrium temperature. So the hot one is going to transfer heat energy to the cold one, okay? And then they'll meet at some middle temperature. Okay? And the question is, this is a little bit of an abstract question. Not what is the mass of either one of the blocks, but what is the relative mass of the 2 blocks? So what is one mass compared to the other? Okay? What is the mass of the copper compared to the mass of the aluminum? Right? There's some ratio. Right? So we're never going to solve for an exact mass, but we're going to solve for like a ratio of masses. Tell you what, too, if this confuses you a whole lot, you can make up a mass for the aluminum like 1 gram or 1 kilogram, and everything would work out. Okay. So I'm going to draw a picture that looks something like this. I have a mass of copper sitting next to a mass of aluminum. Okay. The copper's really hot, the aluminum's a lot colder, and there's going to be a transfer of heat energy. Of do an arrow with a Q, right? So like transfer heat energy from the hot one to the cold one until they reach equilibrium, and then that process stops. So the delta Q of the copper is equal to the negative delta Q of the aluminum. Right? The energy absorbed by the aluminum is lost by the copper. So let's do mass of copper times specific heat of copper times the change in temperature of the copper equals mass of the aluminum times specific heat of aluminum times change in temperature of the aluminum. True? Right. And then change in temperature is final minus initial temperature. So next line, mass of copper times specific heat of copper times final minus initial temperature of the copper is equal to, oh, I forgot my negative sign, equal to negative mass aluminum, specific heat of aluminum, final temperature minus initial temperature of aluminum. Okay. Notice it's the same final temperature on both sides because they're going to reach an equilibrium point. Okay. Now, there are actually 2 unknowns in this one equation, which means we'll never be able to exactly solve it. But remember the question, says what's the ratio of those two variables that I just circled. So I'm gonna go ahead and solve this in terms of variables. Why not? So we're solving for this mass of copper compared to mass of aluminum. Okay. You guys see that's going to be well, specific heat of aluminum times. I'm going to take this negative and just transfer it into. You're going to distribute this negative into here. So go temperature initial aluminum minus final temperature, then all divided by specific heat of copper. Temperature. Did I just? No, we're all right. Temperature final minus temperature initial. The copper. Oh, did I? Yeah. Oops. I meant to do that the other way around. Okay. Well, this will still work. I just wanted positive numbers, but I'll have a negative divided by a negative. So oops, that's okay. It'll still work out. Okay. So specific heat capacity of the aluminum was 0.90 joules per gram Kelvin. The initial temperature of the aluminum was 20 degrees, and the final temperature was 60 degrees. These are the numbers on my paper. Yours are different. Then for the copper, specific heat capacity is 0.39 joules per gram Kelvin, which notice is a smaller heat capacity than it. What did I just do? Did I just? No, we're good. That's how the numbers go. Okay. Then final temperature was 60 degrees, and the initial temperature was for the copper was 100 degrees. Okay. My numbers are okay. All right. And you don't have to convert Celsius to Kelvin because it's the temperature change, right? If we were later on this week, we'll do ideal gas law where we directly multiply by temperatures. So you have to do conversion. Actually, the very next question we'll have to do conversion. Okay, so see, I have a negative over negative. Oops, I didn't need to set up that way, but the negatives are going to cancel anyway. So it's 0.9 times 40, all divided by 0.39 by 40. Okay. I'm looking at a ratio of 2.31 to 1. Okay. So again, the specific masses of either of these materials don't matter. But I need, say I had 1 gram of aluminum, I would need 2.3 grams of copper for all these numbers to play out. Or if I had 1 kilogram of aluminum, I would need 2.3 kilograms of copper for everything to work out. Okay. Give you guys a minute to work that out. All right, how many guys need more time? Need more time. All right, this working out for you guys? Yeah. All right. So we got one more problem here. You do 0.050 joules of work on the coffee in your cup each time you stir it. Right, so let's say like you stir once. What would be the increase in entropy of 125 milliliters of coffee at 65 degrees Celsius when you stir it 20 times? So like give it 20 stirs. Okay, so well, if I was interested in the total work I would do, I would just multiply these two, right? This many joules times this many stirs, right? Well, joules per stir times stirs. But that's not the question. The question is how much entropy. Now remember what entropy is. There's it's this abstract idea that you can actually run an equation on. We're about to run an equation, has units and the whole deal, of either increase in disorder, like increase in randomness. Like when you first pour in the coffee and sugar in this coffee, then it's not mixed very well. But if you start to stir it, all those molecules get really stirred really well, and you can't unstir that, right? So that indicates an increase in entropy. Another perspective on entropy is that the more entropy, the less work is available, the less energy that there is available to do useful work. Right? So the equation that we're going to use for this goes like this. The increase in entropy, delta S, change in entropy, increase in entropy, is equal to the work done, delta Q, divided by the absolute temperature that this process all happens at. Okay. So that's going to be, see, delta Q was 0.050 joules per stir multiplied by 20 stirs. And this all happens at, now I said 65 degrees Celsius, but should I divide by 65? How about this? Celsius is a relative scale. That means, for example, it can go negative. What would happen if you were to divide by a negative number? That would mean that the change in entropy would be negative, like the system is actually becoming more ordered. That's how you would interpret that. But wouldn't that break the second law of thermodynamics? It says that entropy should always be increasing, not decreasing. So what I'm trying to say is that you can't divide by the temperature in a relative scale. You have to use an absolute scale. So I don't want to say 65 degrees Celsius. I want to say how many Kelvin is that? So don't I have to add 273? Or 0.15? This would be joules per Kelvin. Okay, so this many joules divided by this many Kelvin gives me some number of joules per Kelvin. And that's what entropy, that's the unit for entropy, joule per Kelvin. Joules per Kelvin. Okay. You guys getting an option on your paper? Okay, so the 273 comes from converting Celsius into Kelvin. That's right here. So if it's 65 degrees Celsius, so that's like really warm water, right? 65 degrees Celsius plus 273, that's the same thing as 338 Kelvin. Okay? So that's the temperature you need to actually apply to this equation. And the same will be true later this week when we do ideal gas law. You have to plug in Kelvin, because if you scale up temperature by some factor, well, you have to use an absolute scale, which would be the Kelvin scale. It's working out for everybody now?